Welcome to the deep dive. Today we're diving headfirst into how cryptocurrencies actually keep track of everything.
Yeah, the ledger models.
Exactly. We'll be looking at the two main paradigms. You've got the UTXO model, think Bitcoin, Cardano, and then the account-based model, like Ethereum uses.
And what's really interesting is something you specifically asked about is tracing how these ideas developed. How someone involved quite early with the account model concept later became involved in developing Cardano's ETXO model. That's just a fascinating thread.
It really is. And we'll definitely explore the security side too, comparing the, let's say, inherent immutability of UTXO versus that famous historical rewrite that happened with the account model in Ethereum's early days.
Right. So for this deep dive, we've got a good mix of sources. We've looked at explanations of Ethereum accounts, Cardano's extended UTXO, the EUTXO model, some direct comparisons, Bitcoin transaction basics just to ground us in UTXO, and a key research paper, the extended UTXO model.
Okay, so our mission today is pretty clear. Understand that evolution from account-based thinking to EUTXO, get under the hood of the security differences, and see what design choices led Cardano down its particular path.
Sounds like a plan. Where should we start? Account model.
Yeah, let's start there. Ethereum's the obvious example.
Yeah.
So think of it like digital mailboxes, maybe. Each one has an ether balance, sends transactions.
And there are two main kinds, right?
Exactly. You've got your EOAs, externally owned accounts. That's like your personal wallet controlled by your private key.
The ones most users interact with directly.
Right. And then you have contract accounts. These are basically smart contracts living on the blockchain, and they're controlled by their own code.
And both types can do a lot. Hold ETH, send ETH, tokens, interact with other contracts. They're quite versatile.
But they're not identical.
No, definitely not. Key differences. Creating an EOA, your basic user account, is essentially free. And crucially, you initiate transactions using your private key.
So you're in control.
You're in control. Transactions between EOAs are usually just value transfers. Simple enough. It all boils down to that private key proving ownership.
Okay, but contract accounts are different.
Yeah, creating them costs gas, ether, because you're deploying code using network storage.
Like renting space on the blockchain?
Kind of. And they can't start transactions on their own. They only act in response to receiving a transaction.
So they react.
They react. But when they do, they can trigger all sorts of complex actions defined in their code swaps, minting, whatever. And importantly, no private keys for contracts, just code logic.
So if we looked inside an Ethereum account, what fields would we see?
There are four key ones. First up is the nonce.
The transaction counter.
Exactly. It's sequential for each outgoing transaction from an account. Super important, prevents replay attacks, someone just sending your transaction again and again.
Right. Stops them draining your funds. Makes sense.
Then obviously the balance, how much ether the account holds, measured in Wei, the smallest unit.
Like Satoshis in Bitcoin.
Precisely. Then there's the code hash. This is interesting. If it's a contract account, this is a hash, like a unique fingerprint of the contract's code stored on the Ethereum virtual machine.
And if it's just a regular user account, an EOA,
then it's just the hash of an empty string. It tells you there's no code associated with it. That code hash is vital for trusting contracts once deployed. That hash proves the code hasn't changed.
Immutability of the contract code itself.
Right. And the last field is the storage root. Think of it as a summary, a cryptographic root hash of all the data stored by that account. For a contract, this is where its internal state lives. For EOA, it starts empty.
Okay. And getting an EOA in the first place involves generating that key pair, right?
Right.
Private key, then the public key is derived.
Yeah, and your public address, the one you share, is basically a shortened hashed version of that public key.
So that cryptographic hash is like a unique identifier. Change one tiny bit of the input, the public key, and the output, the address, looks completely different.
Exactly. It's all about proving you hold the secret, the private key, to authorize actions for that address.
And this whole account concept, holding a balance, having storage, that was pretty revolutionary for enabling smart contracts, wasn't it?
Oh, absolutely. It was fundamental to Ethereum's early success and the explosion of decentralized applications. Having these programmable entities with memory, with state, opened up so many possibilities.
But as we mentioned, and as our listener highlighted, it wasn't without its challenges, especially regarding security and the permanence of the ledger history.
Which leads us nicely into the alternative.
Yeah, let's switch gears to the UTXO model, Bitcoin's foundation, and also Cardano's, though with a twist. So forget accounts with balances for a second.
Right. UTXO stands for unspent transaction output. It's less like a bank account balance and more like having a collection of individual digital coins or banknotes in your wallet.
Okay, so transactions work differently then.
Totally differently. A transaction doesn't just debit one account and credit another. Instead, it consumes existing UTXOs, spends those specific banknotes, and creates new UTXOs as outputs.
So inputs get used up, outputs get created.
Precisely. Each output has an address, the lock, and a value. To spend it later, you need the signature corresponding to that address, the key.
And a key point is that each UTXO is spent only once, and you have to spend the whole thing.
Exactly. If a UTXO is worth 10 coins and you only want to send 7, your transaction will consume the 10-coin UTXO, create a new 7-coin UTXO for the recipient, and create a new 3-coin UTXO as change sent back to an address you control.
Okay, that's the basic UTXO. Now, Cardano's ETXO, the extended model, how does that build on this?
It introduces a couple of really key innovations. First, it generalizes what that address or lock on an output can be. Instead of just being tied to a public key signature, the lock can be defined by arbitrary logic, a script.
So it's not just unlock with this key, it could be unlock if these conditions are met.
Exactly. Much more flexible. The script dictates the conditions for spending. The second big thing is that outputs can carry additional arbitrary data alongside the address and value. This is called the datum.
And that datum is the key to stateful smart contracts on EUTXO.
That's the breakthrough. It allows you to pass state information from one transaction to the next, attached to the UTXOs themselves, without needing a global shared state like in the account model.
And the research paper we looked at, the extended UTXO model, credits the team at IOHK. Names like Chakravarti, Chapman, Wadler are mentioned with formalizing this.
Yes, the paper makes it clear that the EUTXO model in Cardano is an IOHK development. And, connecting back to our listeners' interest, while not explicitly stating one person's journey, it acknowledges that this work builds on earlier thinking about more expressive blockchain models. Some folks involved there certainly have deep roots tracing back to, related fields and potentially earlier blockchain concepts.
So it represents an evolution of thought within that research group.
You could certainly see it that way. And this EUTXO approach aims for several advantages. Better security, potentially better scalability, because validation can be more localized.
More privacy, too, sometimes.
Potentially, yes. And transaction validation becomes deterministic, because everything needed to check if a transaction is valid, the inputs it's trying to spend, the scripts, the datum is contained within the transaction itself or referenced directly by it.
You don't need to know the entire current state of the blockchain network.
Not in the same way as the account model. You can basically check if a transaction will work off-chain before you even submit it. This predictability is a big deal. It also helps with parallel validation, checking multiple transactions at once, and can lead to more predictable fees.
Okay, this brings us squarely to the listener's core question. Trust and security. UTXO versus account model, especially thinking about altering history.
Right, and this is where the UTXO model really shines in terms of, its inherent immutability.
Because it's just a chain of outputs, each spent once.
Exactly. Think of it like links in a chain. Each transaction consumes specific previous outputs and creates new ones. Its validity depends cryptographically on those previous outputs existing and being unspent. Trying to go back and change an old transaction
Would break the chain.
It would invalidate everything that came after it, which depended on its outputs. The cryptographic links the transaction IDs. The references would all be wrong. Those outputs, once created and then spent, are gone, used up. Immutable in that sense.
Which contrasts pretty sharply with the Ethereum situation, the hack, and the subsequent hard fork.
Very sharply.
Yeah.
That event demonstrated that in the account model, under, let's be clear, exceptional circumstances and requiring massive community consensus.
A kind of social consensus override.
Precisely. It was possible to effectively rewrite the ledger state. They rolled back the blockchain to a point before the hack, essentially erasing the theft by altering the state of the affected contract account and related balances.
So the history wasn't absolutely immutable in practice there.
It highlighted a trade-off. The account model's structure, perhaps, allowed for this intervention, which some saw as necessary to correct a disaster, while others saw it as a violation of the core principle of immutability. It was hugely controversial, as you know.
And doing something similar in a UTXO system seems architecturally much harder.
Oh, much harder. You're not just suggesting a balance in one account. You'd have to somehow reconstruct a whole series of transaction outputs and potentially invalidate vast swaths of subsequent unrelated transactions that might have indirectly depended on the chain's integrity. It's structurally designed against that kind of rollback.
And you mentioned stateless validation earlier. How does that play into security?
Well, because validating a UTXO transaction primarily involves looking at the transaction itself and the specific UTXOs it consumes, it simplifies the process. You don't have the same complexities around accessing and potentially conflicting with a large shared global state that changes with every block. This reduces the surface area for certain types of bugs or attacks related to state management.
Interesting. So moving beyond the core security aspect, the EUTXO model seems designed to get the best of both worlds in a way. The security of UTXO plus more smart contract power.
That's definitely the goal. To bring that expressiveness, that flexibility for complex applications that Ethereum's account model pioneered, but bring it to the UTXO paradigm.
And doing it without shared mutable state is key.
That's a major point the research paper emphasizes. By avoiding that shared state, where multiple contract calls might try to change the same piece of data concurrently, they argue it simplifies the whole model and potentially avoids complex bugs, like reentrancy attacks referencing the DAO hack again as a cautionary tale of shared state risks.
Right. Those complex interactions can be hard to predict.
Extremely hard. EUTXO aims for more predictability.
And the parallel processing potential we touched on, that's a big scalability argument for UTXO-based systems, isn't it?
It is. If transactions don't interfere with each other's state in complex ways, you can potentially validate many of them in parallel on multi-core processors, which is harder when everything depends on a single sequential state machine.
Were there earlier attempts to add this kind of programmability to UTXO?
Yeah, the idea isn't entirely new. There were concepts like Bitcoin covenants discussed years ago, proposals to add rules about how future transactions could spend certain Bitcoin outputs. But EUTXO, especially with the addition of the datum for carrying state, offers a much more integrated and arguably powerful approach.
So for listeners wanting to go deeper, checking out Plutus, Cardano's smart contract language.
Definitely. Seeing how Plutus code actually defines those locking scripts and works with the datum would really illustrate how EUTXO operates in practice.
It really does boil down to that fundamental design choice, doesn't it? How do you best balance flexibility for developers building apps with the absolute need for security and that reliable, unchanging history?
It's the core tension, yeah. Different philosophies, different trade-offs. Account model offers a perhaps more intuitive model for developers familiar with object-oriented programming, but arguably introduces state management complexities. UTXO EUTXO offers this inherent immutability and potential for parallelism, but requires maybe a different way of thinking about programming state transitions.
Okay, so let's try and summarize the key takeaways from our deep dive today. We've charted a path from the account model concepts to the extended UTXO model in Cardano.
Yeah, highlighting that evolution and the thinking behind UTXO's design.
We've also really contrasted the security postures, the UTXO model's strong resistance to history rewrites versus the account model's demonstrated flexibility, let's call it, under extreme duress.
And emphasizing how those architectural differences, stateful accounts versus stateless outputs with data, lead to different strengths and challenges.
And it really shows this ongoing learning process in the blockchain space, doesn't it? Refining ideas, trying to improve on previous models.
Absolutely. The journey from those early days to something like EUTXO shows constant innovation.
So maybe a final thought for you, the listener, to mull over. Given these trade-offs we've discussed, stateful accounts versus these stateless data-carrying outputs, what might the next step look like? What future innovations could potentially bridge these gaps even further, offering systems that are even more robust, expressive, and secure?
That's the billion-dollar question, isn't it? Where does blockchain architecture go from here?
Some to think about. Thanks for joining us on this deep dive.